Okay, so for this example, we want to describe the level curves of the function and sketch a contour map of the surface. All right, and we have our xy plane here already to help us sketch the contour map. So if you're following along, be sure to draw yourself an xy plane as well. But our function here is f of xy is equal to y squared minus x squared. Okay, so the first thing we want to do is figure out what the level curves will look like for the surface represented by this multivariable function. That's what the problem means by describe the level curves. We want to figure out what general shape are we going to get for our different values of c. In our first example, all of our level curves were circles, but that's probably not going to be the case here. And so let's take a look. What we want to do is set our function equal to a constant value c. All right, so we're going to have c is equal to y squared minus x squared. And so then what we want to do is try to get this equation in the form of some type of curve that we recognize. And the first thing I'm going to do is just flip the two sides of the equation. This just helps me recognize the equation a little bit better when I have the variables on the left side. So I'll write y squared minus x squared is equal to c. And then notice that if we were to divide both sides of the equation by this constant value c, our equation would be in the form of a hyperbola, right? Dividing both sides by c will give you y squared divided by c minus x squared divided by c is equal to 1, because c divided by itself would be 1. And this right here would be the equation of a hyperbola. It looks very similar to the equation of an ellipse, except one of the two terms for y squared or x squared is negative. In this case, the x squared term is negative. All right, so our level curves here for this function will be hyperbolas. That is what we have found here. That's how we can describe the level curves. All right, so once again, this is always your first step. Set your function equal to that constant value of c, and then try to manipulate the equation into a form such that you recognize the type of curve that the equation represents. Okay, in this case, hyperbolas. But now let's actually find some of these level curves. Let's start plugging some different constant values in for c. And so I always like to start with c equals 0. That might seem like a problem at first, because if you're looking at this form of the equation, you can't divide by 0. But if you go back one step to this equation, you can have the equation y squared minus x squared equals 0, right? That is an equation. You might not quite remember what that represents, but what that is a degenerate hyperbola, okay? Instead of your typical hyperbola, which has two different curves, a degenerate hyperbola, specifically this one, y squared minus x squared, is a graph where you have the line y equals x and y equals negative x. Okay, that's what this equation represents, right? You could solve for y squared here. You'd have y squared equals x squared, take the square root of both sides, and y equals plus or minus x. So that gives you the two lines y equals x and y equals negative x. Okay, so that's just a degenerate hyperbola. That's our level curve for c equals 0. But then let's move on to another value of c. I'm just going to move up by 1 to c equals 1, and then keep that same spacing for all of my constant values. So let's look at c equals 1. Now we can plug that value of c into this form of the equation, but really it's just going to be the same thing as up here, because y squared divided by 1 is y squared, and x squared divided by 1 is x squared. So we do just get y squared minus x squared equals 1. And that would just be a regular hyperbola. And so then let's look at c equals 2. If you plug 2 in for these two c's, you get y squared divided by 2 minus x squared divided by 2 equals 1. And then let's do one more. Let's look at c equals 3, and you'll get y squared divided by 3 minus x squared divided by 3 equals 1. All right, we just replaced each of these c's with 3. And so these three equations, or these three level curves, are all regular hyperbolas. They just have slightly different shapes because of those denominators changing for y squared and x squared. We'll talk about how to graph those in a moment, but before we do, we can actually look at negative values of c here as well. We couldn't in our first example, because our function was a square root function. There's no way to output negative values, but in this case, y squared minus x squared can be negative, right? This constant value of c that would result from this subtraction could be negative because the value of x squared could be bigger than y squared. So it does make sense to look at some values of c here that are negative. And when you can do that, you should at least look at 1 or 2. It won't always be helpful, but many times it will be. So let's look at a couple here. Remember to keep the same spacing. So let's go from c equals 0 to c equals negative 1. So for c equals negative 1, something interesting is going to happen here. We're going to divide both of these two terms by negative 1. So the signs are going to change. Instead of x squared being the negative term, y squared will be the negative term. So I'm going to rewrite the equation like this. You'd have x squared minus y squared equals 1. All right, the y squared term is now negative and the x squared term is now positive, and I just flip their placement in the equation so that it looks a little bit nicer. We now have x squared minus y squared rather than y squared minus x squared when c was positive 1. All right, and if we were to look at c equals negative 2 and negative 3, a very similar pattern is going to occur. We're going to have the same equations that we did for c equals 2 and c equals 3, except the signs of these two terms are going to flip. For c equals negative 2, you'll have x squared divided by 2 minus y squared divided by 2 equals 1. And then for c equals negative 3, you'll have x squared divided by 3 minus y squared divided by 3 equals 1. All right, that's what we would get when plugging c equals negative 2 and negative 3 into this equation. And so now that's enough. I think we have plenty of level curves here to graph in this plane to get a sketch of the contour map of the surface represented by this function. And so let's start with c equals 0. As I already mentioned earlier, that is a degenerate hyperbola, which in this case will just be represented by two lines, y equals x and y equals negative x. So let's graph those here. This will be y equals x and y equals negative x. And so that right there is our level curve for c equals 0. But then let's move on to c equals 1. How do we graph y squared minus x squared equals 1? That is a hyperbola, specifically one that is directed along the y-axis because the y term is positive. All right, if you don't remember how to graph your conic sections, you're going to get a quick little review here. Whichever variable term is positive, the corresponding axis is the one the hyperbola is directed along, and then the square root of whatever the positive term is being divided by, that will give you the values of the intercepts along that particular axis. All right, so in this case, y squared, the positive term is being divided by 1 technically, and the square root of 1 is plus or minus 1, so we know that the two curves for this hyperbola will be directed along the y-axis and cut through y equals 1 and y equals negative 1. All right, so if this is y equals 1 and this is y equals negative 1, one of the curves for that hyperbola will look like this, and the other one will look like this. All right, that is c equals 1. Now let's move on to c equals 2. The y term is still positive, so we're still going to be directed along the y-axis, but this time the square root of 2 will give us our y-intercepts, and as a decimal, the square root of 2 is approximately 1.4. So assuming that this is y equals 2 and y equals negative 2, about halfway to 2 in each direction will be the intercept for the curves of this hyperbola. So one of them would look something like this, and the other one would look something like this. All right, that is the level curve for c equals 2. Now let's look at c equals 3. The y term is still positive, so we're still directed along the y-axis, but now the square root of 3 will give us the intercepts. And so as a decimal, the square root of 3 is approximately 1.7. So we're going to be even closer to 2 in each direction. So one of the curves for the hyperbola will look like this, and the other one will look something like this. That will be c equals 3, or the level curve for that value of c. And so that takes care of all of our level curves for positive values of c. But what about our negative ones? Negative 1, negative 2, and negative 3. Well, in each of these equations, the x term is positive, but everything else basically remains the same. So we're going to have the same hyperbola as we just drew here, but now they're going to be directed along the x-axis. All right, so for c equals negative 1, we'll have two curves with x-intercepts of 1 and negative 1. Then for c equals negative 2, the intercepts will be plus or minus the square root of 2, so 1.4 in each direction. And then for c equals negative 3, the intercepts will be plus or minus the square root of 3. So let's graph those hyperbolas here. This is x equals 1 and x equals 2, and then x equals negative 1 and negative 2. For c equals negative 1, we'll have a curve like this and a curve like this. That's for c equals negative 1. And then for c equals negative 2, we'll have an intercept of about 1.4. So one of the curves will look like this, and then in the negative direction, the other one will look like this. That is c equals negative 2. And then finally for c equals negative 3, the intercept is about 1.7, which is the square root of 3. So that's one of the curves, and then here's the other one in the negative direction. That will be c equals negative 3. All right, and so now we're done. That is the contour map that features all of the level curves that we found here. This gives us a way to sort of visualize the shape of the surface represented by this function. All right, and if you were to look at the surface represented by this function, here's a 3D render. Once again, I've included level curves on the surface. I've included more than we drew in our contour map just to give you an even better visual. But here you can now actually see the shape of the surface, and then when you look at it from the top down, so that you're only looking at the level curves from the perspective where you're looking at the XY plane. So think of it as squashing the surface into the XY plane. Now you can see all those level curves, which should look very similar to the contour map that we sketched here. Okay, and so that's it for this